Oftentimes, rocket scientists need to express the path of the rocket as a function of time and yet still use x and y to describe the position. Therefore, we need to use parametric equations to link x and y with t for time. Hi, my name is Jason Rosenberry, and that's what we will be looking at in today's lesson, parametric equations. Let's start with a definition of a relation. A relation is a set of ordered pairs, x, y, of real numbers. The graph of a relation is the set of points in the plane that correspond to the ordered pairs in the relation. Sometimes x and y are functions of a third variable t, called a parameter. Let's look at a definition. Parametric curve, parametric equations. If x and y are given as functions, x equals f of t and y equals g of t, over the interval of t values, then the set of points defined by x, y equals f of t, g of t, defined by these equations, is a parametric curve. The equations are parametric equations for the curve. Given x equals t, y equals 1 minus t, and t is in the closed interval from 0 to 1, Part A, graph the curve. What are the initial and terminal points? Indicate the direction the curve is traced. Part B, find the Cartesian equation for a curve that contains the parameterized curve. What portion of the Cartesian equation is traced by the parameterized curve? Here we have the graph of our parametric equation using our graphing calculator. Recall that the values of t start at 0 and go to 1. So when we let t equal 0, that gives us the ordered pair x equals 0, y would equal 1 minus 0, or 1. So the initial point would be 0, 1, which is indicated on the graph. Now we go to the other endpoint of our interval, positive 1. Letting t be positive 1, we obtain the point 1, 1 minus 1, 0. So the final point, or terminal point, is 1, 0. The graph is then traced in this direction. And now we'll try to find the Cartesian equation for a curve that contains this parameterized curve. Well, if we find the equation of the line that passes through these 2 points, we get y equals negative x plus 1. Therefore, the graph y equals negative x plus 1, allowing x to go from 0 to 1. So the portion of the Cartesian equation y equals negative x plus 1 from x equals 0 to 1, that is the portion of a Cartesian equation that is traced by the parameterized curve. Some relations have parameterizations that can be standardized. Let's look at 2 of these. Circles. A parameterization x equals a cosine t, y equals a sine t, is a parameterization of a circle with center located at 0, 0 and radius a. We can prove this by showing that x squared plus y squared equals the same thing as, substituting in for x, a cosine t, substituting in for y, a sine t. We would have a cosine t squared plus a sine t squared, which results in a squared cosine squared t plus a squared sine squared t. Factoring out a squared, we have a squared times the quantity sine squared t plus cosine squared t. Sine squared t plus cosine squared t is equal to 1, giving us a squared. So we have x squared plus y squared equals a squared, which is the standard form equation of a circle whose center is at the origin 0, 0 with radius a. Let's try an example. Given x equals cosine t, y equals sine t, and t is in the interval, closed interval, from 0 to pi, a, graph the curve. What are the initial and terminal points? Indicate the direction the curve is traced. B, find the Cartesian equation for a curve that contains the parameterized curve. What portion of the Cartesian equation is traced by the parameterized curve? So here we have our parametric equation, x equals cosine t, y equals sine t. T again is in the closed interval from 0 to pi. Using our graphing calculator, here we have the graph of this parametric equation. Let's find the initial point. The initial point occurs when t is equal to 0. Substituting 0 into the parametric equation, x is equal to cosine 0, y is equal to sine 0. The cosine of 0 is 1, and the sine of 0 is 0. So our initial point is 1, 0. To find the terminal point, we let t equal pi. So again, the cosine of pi is -1, and the sine of pi is 0. So the initial point is at 1, 0. The terminal point is at -1, 0, and the curve is being traced in this direction. Now let's find the Cartesian equation for this parametric equation. Well, here we have a circle whose center is at the origin, and it appears as if the radius of this circle is 1 unit. So we will start with x squared plus y squared is equal to 1. That would give us the full circle, And as we can see here, we only want the top part of the circle, or semicircle. So solving this equation for y, we would get y equals the square root of 1 minus x squared, plus or minus. The positive root gives us the top part of the circle. The negative root gives us the bottom part of the circle. So since we only want the top part of the circle, then we only want y equals the square root of 1 minus x squared from x equals -1 to +1. The other standard parametrization we want to look at is one for an ellipse. Ellipses. A parameterization, x equals a cosine t, y equals b sine t, is a parameterization of an ellipse with center 0, 0. Let's try an example. Given that x equals 4 sine t and y is equal to 2 cosine t, where t is in the closed interval from 0 to pi, A, graph the curve. What are the initial and terminal points? Indicate the direction the curve is traced. B, find the Cartesian equation for a curve that contains the parameterized curve. What portion of the Cartesian equation is traced by the parameterized curve? So here's our parametric equation, x equals 4 sine t, y equals 2 cosine t. T is in the closed interval from 0 to pi. Here on the left we have the graph of this parametric equation using our graphing calculator. And the first part of our question is find the initial point. So that occurs when t is equal to 0. So substituting 0 into the parametric equation, x would equal 4 sine 0, which is 0. Y would equal 2 cosine 0, which is 2. So the initial point is at 0, 2. To find the terminal point, we'll now let t equal pi. So 4 sine pi is 0. Y equals 2 cosine pi, which would be -2. So that point is here. So the graph is being traced in this direction. Now let's find the Cartesian equation for the whole ellipse, the entire ellipse, and then we'll see which part is being traced. Let's start by dividing both sides of this equation by 4. That gives us x over 4 is equal to sine t. Dividing both sides of this equation by 2 gives us y over 2 is equal to cosine t. Now we'll square both sides of these equations, giving us x over 4 squared equals sine squared t. Second equation, squaring both sides, we would have y over 2 squared equals cosine squared t. Now adding these two equations together, we get x over 4 squared plus y over 2 squared equals 1. And now we'll solve this equation for x, giving us x equals 2 times the square root of 4 minus y squared. So there's the Cartesian equation for the right-hand side of our ellipse. And we also want to say that the y values will go from positive 2 to negative 2. Let's try some other examples that are not necessarily circles or ellipse. Given x equals 2t minus 5, y is equal to 4t minus 7, and t is between negative infinity and positive infinity. Part A, graph the curve. What are the initial and terminal points? Indicate the direction the curve is traced. So using our graphing calculator, here's the graph of our parametric equation. Because t goes from negative infinity to positive infinity, there are no initial nor terminal points. The direction that the graph is traced in, going from left to right, from negative infinity to positive infinity, the graph would be traced in this direction. Part B, find the Cartesian equation for a curve that contains the parametrized curve. What portion of the Cartesian equation is traced by the parametrized curve? Let's first take our x equals equation and solve it for t. So we have x equals 2t minus 5. We're going to solve this for t. So we would have 2t is equal to x plus 5. Therefore, t is equal to x plus 5 all over 2. We will now substitute our t in for t in the y equation. So that gives us y is equal to 4 times t. T is equal to x plus 5 over 2 minus 7. That gives us y equals 2 times the quantity, x plus 5 minus 7. Y equals 2x plus 10 minus 7 is plus 3. So the parametrized curve traces all of the line defined by y equals 2x plus 3. Find a parameterization for the line segment with endpoints at negative 2, 1 and 3, 5. We'll start with this point, negative 2, 1, and we'll set up the following system of equations. We know that the x-coordinate must equal negative 2 plus a times t, and we know that the y-coordinate would equal 1 plus b times t for t equaling 0. So as you can see, if we substitute 0 in for t, we get x equals negative 2 and y equals 1, which corresponds to our first point. Now let's take each of these equations and solve them for t. Solving the x equals equation for t gives us x plus 2 over a is equal to t, and solving the y equals equation for t, we get y minus 1 over b is equal to t. Now we'll let the increment of t increase by 1. So let's let t equal 1. So this implies that x plus 2, and now we're going to start using information from the second point, so we'll let x be 3. So we get 3 plus 2 over a equals 1. And again, we're letting t equal 1 as well. So the y coordinate is 5, so we would have y minus 1 over b is equal to 1. Well, this implies 5 over 5 gives us 1. So a has to equal 5, and also 5 for the b value. 5 minus 1 is 4. 4 over 4 gives us 1. So b would have to equal 4. There we found the a and the b needed to substitute those values into this equation. So after making those substitutions, x equals negative 2 plus 5t, y equals 1 plus 4t, with t being in the closed interval from 0 to 1, is the parameterization of the line segment with initial point negative 2, 1 and terminal point 3, 5. Find a parameterization for the ray with initial point 2, 3 that passes through the point negative 1, negative 1. Pause the video while you work on this problem. When you are finished, restart the video and check your solution. Again, there are many possible answers for this problem. I'll just show you one in particular. We could let x equal 2 minus 3t, and by doing so, y would have to equal 3 minus 4t. And then for the traced portion of this line to be coordinated with the ray that starts at 2, 3 and goes to negative 1, 1, here we would let t be greater than or equal to 0. In this lesson, we explored parametric equations and their graphs, as well as applications of parametric equations. Be sure to work the exercises that your teacher assigns. We'll see you next time.